Hello, everyone. Thanks for coming to my talk. I know I kind of have some stiff competition with the Matplotlib talk, so I appreciate you coming out and seeing me today. What I'm going to talk about is how me and my company MaxPoint, along with all my great colleagues, have actually used PyData and put it into production and got it into the hands of our users. Just to introduce myself once again, Josh Howes. I've been at MaxPoint for 3.5 years. I'm a senior manager there, still pretty hands-on though, working on a variety of problems from geospatial analytics to traditional kind of machine learning prediction classification problems, causal inference, those types of things. And this is my company, MaxPoint. We're a sponsor here. I'm sure you probably accidentally stumbled into a couple of our other talks today. What MaxPoint does actually is we're a marketing technology company. We help our brands, large retailers, advertising agencies, be smarter about how they spend their marketing dollars, but you guys probably really don't care about that. What you care about, and what I think makes us interesting for this crowd, is that we have large data sets and interesting data sets. We're HDFS Hadoop shop, and we have hundreds of terabytes of data from everything from how we bid in the RTB space for delivering ads, to geospatial data sets, again, to point of sale data. And we have interesting problems, and we use the PyData stack to solve them. So we're trying to predict who will respond to an advertisement online. How do people move about physical space, and does that tell us something interesting? Are there things about the data that we collect that tell our customers how they should better spend their money? So I'll talk a little bit about our software ecosystem and kind of frame what production actually means and what kind of constraints we're working with when we're talking about production. But the key thing is that we have kind of two main stakeholders in our product software stack. First is the data science team. And our data science team does a variety of things. We do kind of data analytics and data analysis to help guide the business. We do methods research, but we also actually implement our ideas in software that lives in production. And we do that largely in Python and using the PyData tools. A couple of examples here are, we're using classifiers to predict the effectiveness of advertising. We're doing topic models on web content. We're building geospatial models and many more examples. The other people that are putting code into production at MaxPoint is our traditional software engineering group. And this group is really responsible for all other aspects of the software, including system health and performance, all the non-functional requirements that people that are in the data science domain just don't care about. They call the ilities, availability, reproducibility, accessibility, those type of things, logging, monitoring, system health. And they do many more things as well. But we come at the problems from very different perspectives. We're very much focused on how do we produce analytical pieces and compare that to how does this largely fit into a bigger system. So we have kind of these two groups who are largely thinking about different things and approaching software development from different worldviews. And we largely have different software structures on top of it. I have a beard, so the data science guy is the bearded guy. So we're largely using Python, although we will use R, and I think we've even toyed a little bit with Julia and some other languages as well. But basically, we're using the tools that make us most productive doing data science challenges. And we largely are not thinking about the other pieces of the puzzle that the software engineering group is caring most of their time about. On the other side, our engineer group is largely working in the JVM, and that includes both Java as well as kind of a recent plunge into Scala. We have some Clojure in our code base. We have C++ on our high-speed systems. Some of our front-end systems are in C#. And there's really actually very little overlap traditionally in types of tools and approaches we've taken to how we implement software. And so this is actually causes some problems when you want to help put code into production. You kind of have a couple different options, and they all have pretty big trade-offs, because what we really want is we want to be able to adapt quickly and get things to market quickly. We want to make sure that we keep both sides happy. We want analytics to be able to feel like they're contributing. We want software engineering to feel like the system's in a good state and they don't have to be called at 3 o'clock in the morning because something breaks. And we still want to make sure we have all these non-functional requirements built in. And most importantly, I think we really want to make sure we minimize the opportunities where we have to rewrite code. Because the option where we implement an algorithm and hand it off to someone else to implement in Java or Clojure, one is pretty inefficient and it hurts that time to market, but also is very, very difficult in some circumstances. Sklearn, for example, is a fast-moving, evolving library that has a lot of machine learning algorithms. Finding a sister library in Java that implements the same things is just it's impossible, actually. And so being able to kind of make sure we're not having to translate these types of things, writing new custom code and not relying on the community is something that we really want to avoid. So I'll talk about kind of two big workloads that we're going to talk about today in terms of how we've tried to bridge that gap. The first one is just the interactive workload. These are kind of our real-ish time processes that require interaction with an end user. And so you can imagine someone is sitting in front of their computer, they're asking for data likely parameterized by some settings, and they're expecting responses back in nearish real time. And so how we've approached this at MaxPoint is by building what I'll just call analytics microservices. And microservices is a pretty kind of popular concept in software engineering, but basically what it means is we would prefer to build a lot of small services with very compact APIs rather than one monolith service that requires a lot of maintenance and difficulty making changes in releases. And so how we've done this, both in trying to preserve the Java and the non-functional world from software engineering and all the access to all the PyData goodies that our data scientists like, is we've kind of used this wrapper approach between our service layers. So we've implemented it with Apache Thrift, which I'll talk a little bit more in a second, but it's basically providing the RPC calls between the Python layer and the Java layer. And what this really has allowed us to do is we can put all those non-functional requirements that our data scientists don't care about, hide them up in the Java layer, and the analytics and the things that we're doing in Python is really isolated exclusively to the things that our data scientists care about. It also really makes it much easier for us to reuse the logic that our engineering counterparts have implemented. So other services that we have within the organization are all written in Java, and so they can pull those things in and support analytical products with all the non-functional requirements, even though all the core logic is implemented in Python. So this is a very simplistic version, but basically what happens is we have this Java layer that is basically calling out to the PyData layer through Apache Thrift. And how we've kind of made this work is we actually have a pool of processes that are running our Python code. The Java layer is doing all the kind of queue management, making sure that we're load balancing across these Python processes, and ultimately providing the public interface to all our clients. So nothing knows about the private pool that is implementing the Python stack outside of this public service that's then made public to the rest of the service-oriented architecture that we have in-house. Out of curiosity, how many people are familiar with Apache Thrift, just so I can get a sense of the audience? Have people used it or seen it? Okay, a smattering. So basically what Apache Thrift is this remote procedural call language, and it is a language in that it has its own DSL, and the DSL basically allows you to define your service in Thrift, and it will handle all the translation and marshalling to various libraries that need to use it. So you would end up defining your service, and this is an example just from Thrift documentation, where you actually define your service in this DSL as a .thrift file. You're defining everything from your namespaces to custom enums to structs and complex data types, exceptions in this Thrift file, ultimately implementing your high-level services and the methods that they're going to support. And then what happens, you run a tool, which is thriftgen, and you tell it which bindings you actually want to produce. So this is pretty cool in a lot of ways, although there is some problems in that you're dealing with kind of the lowest common denominator in a lot of the things that you have here. Any kind of nice abstractions that you may have in Python, if they're not implemented in Java, well, we're kind of in some trouble from Thrift's perspective. So it kind of ties your hands a little bit in that you're kind of working with these structs and these primitive types, but it actually does a lot of the marshalling. I think this is a pretty interesting approach, especially if you're considering the other option, which is commonly used, is implementing REST services. REST services, you still have to worry about all the marshalling and translating of the data. Thrift actually takes care of a lot of this stuff for you. So when you run this thriftgen, it actually prints out the stubs. It produces out both a service layer and a client layer to be able to talk back and forth to these things. And so in this example, this is the server layer, which is basically implementing these methods. There's a lot of code that's not shown here, and all these thrift.transports, shared.ttypes that kind of handles all the marshalling back and forth and the getting it across the wire to the other services. But it gives you these nice templates for which you can then implement. And in any of these methods, you can start importing your NumPy, your Pandas, your Sklearn to be able to implement. Similarly, it also, this is a little small, but I think it shows the purpose, which is it also implements your service code, or your client code, excuse me, which is how would you actually connect to this service. So the idea is that it's handling the protocols, the transport layers, the sockets layers for you, and you generate this in both Python and Java, and these layers can talk to each other. So what were kind of some lessons learned from this approach? I think there's some really kind of cool things about doing your interactive workloads in this manner. One, it really helped us separate the pieces of the logic between engineering and the data science community. We can have people that are focused on data science and people that are focused on engineering, and they're able to actually work in parallel a lot more effectively. It also, as I mentioned, allowed us to share more work and have kind of some reproducible code. We can keep all our core logic for the non-functional requirements in the Java world. We don't have to move things over to Python to have Python services, and kind of try to keep those things in sync would have been a nightmare. But there are some negative things. It's also often very hard to actually define what this analytic microservice is. And there's what I'll call analytic scope creep around how much work the thin Python layer should actually be doing. A good example would be just data access. Should that be done by the Java service, or that should be done by the Python service? Those are the kind of the tough decisions you have to make when you're doing this model. And still, you're actually having to do some implementation in both places. Even if it is doing this thin shim layer communicating back and forth, it is kind of still a double implementation layer. And that stinks, right? And Thrift is easier. It's definitely easier than if you were trying to do this yourself, but it isn't trivial nor easy. You do have to start to learn this other Thrift spec language, although not complicated. It's still some cognitive load that you're taking on when you're talking about your service. You have to think a little bit more about how you structure your return results because you're using these structs and these other kind of more easily translatable data structures that talk across code. And so it's not simple and trivial, but it actually allows us to do a lot of things. So the next part, I'll talk about batch workloads, which is where most of our effort is actually spent, and how we are using Python there. So kind of the basic approach here we can take is we just do everything that we're going to do in terms of using NumPy Pandas and just processing it locally. We'll use a single machine, we'll install our content environments there. Any data that's requiring access to our large data, we'll sample, we'll pick some smaller amount of data, pull it down to this machine, crunch on it, push it back up to our cluster. That works reasonably well, and especially because we can stay in the Python world for certain workloads. So what I'm showing here on this slide is actually IBIS. IBIS is a project that Cloudera is working on that works with their real-time SQL engine Impala. And IBIS allows you to write things that looks a lot like Pandas. And what will happen is it basically compiles these instructions into the SQL query that you would see here that would be executed on the cluster. So you actually get some remote capability, still written in Python, can pull it back locally, working in Pandas. The switching costs are relatively small. And the IBIS, the main author of IBIS is Wes McKinney, so he does try to borrow a lot of the concepts around Pandas. And so you'll see a lot of the same structures. It's nice in that you're not switching between writing these big long SQL strings in your code, which are hard to debug, hard to change, hard to parameterize. You're actually writing code that looks like the types of code that you're running before. But the problem is when you actually can't do something locally and you're doing research and all of a sudden, oh, the thing that I think would scale well and I can run on one machine actually can't. And so what happens now is we have to get someone to rewrite it. And so we've invested some effort in trying to make that easier and parameterizing models and allow to hand off models written in Sklearn to implementing models that are actually implemented in Clojure for Cascalog running on Hadoop. But that is really kind of quite inefficient. It slows our time to market and it makes things a little bit more difficult. So, what have we learned from kind of doing this local approach? The big thing is that there's some really nice features. One, you're going from an environment where you're very familiar in your research spec. When you're writing Pandas, you're working on a notebook, you're pulling data down, you're doing your analysis, to make it into a production job. You basically are just scheduling that script to run parameterized by whatever your model, maybe it's a timestamp, and that's pretty much it. You're not doing this kind of big conversion to go from production, and that speeds up some cycles. But the idea between working at a big data company is the one thing you should learn is that it's really bad to bring your data to your code. Your data is big, gigabytes, terabytes. Your code is small, kilobytes, megabytes. So you much rather move your code to your data than vice versa, and that's what we're doing in these local environments. And it also, really actually requires you to have some pretty beefy hardware. And when you have beefy hardware, it actually requires you to share resources, and which causes its own problems. And I think you can get a little sloppy in your project dependencies when you're doing this. If you're going quickly from development to production, how do you make sure you have the right version of Pandas? How do you handle all these packaging is not trivial. So the next thing is, well, how can we do this still writing Python and bring the code to the data? And one of the things we've tried at MaxPoint in limited amounts is actually streaming MapReduce. And what that does is it allows us to actually bring our Python packages to the cluster. How you implement it is you basically write a Python script that either works on the mapper side or the reduce side of the job, and the Java layer that runs MapReduce is calling out to these scripts. And so basically how it works is this: is you have Hadoop in the Java layer that's doing kind of reading your input off your HDFS cluster. In the map stream, it's calling out through standard in, standard out, piping that back through the Java layer, who takes it to the reduce stream, handles all your shuffling, back through standard in, standard out to your reduce layer, which is in Python, back into the Java layer, out to your output layer. And so if the data flows like that, as you can tell, you're working in through standard in and standard out, and actually you, as the developer, is writing into standard in and standard out. And so this is what your code ends up looking like, right? For a line in standard in, do something with this nasty line of text. That works okay if you're working with something like CSVs. You want to use some other type of data structure, Parquet. Things start to kind of break down there. So this is very low-level MapReduce programming at this point, and largely we've moved past this. I think as a community in the big data space, as well as at a company at MaxPoint. But this is how typically you'd have to do it. And you'd basically just be calling out through Hadoop with these mappers and these reducers written in Python. So, what are kind of the lessons? One, it's really opens you up. Even though it's more painful, it really opens you up to being able to do more interesting things because you're no longer constrained to the RAM or the resources that you have in a single machine. You can now run bigger, nastier models. And it kind of fits well. It's a supported part of the MapReduce ecosystem. The streaming API is one of the APIs of MapReduce. So you're actually using vetted tools, although it does feel a little ugly. But again, you're running into the packaging problem around how do you get your code to all the nodes on the cluster now. That's a challenge. And you having to write code that's relying on the low-level standard in, standard out interfaces, which again I would say is not fun. So enter Apache Spark. We've made a big push over the past year to move to Apache Spark for our processing pipelines. And for those of you who are not familiar with Apache Spark, basically it's this big compute platform. It came out of some work at the AMP lab at Cal Berkeley. But what's nice about it from our workloads is that it actually has multiple APIs supported at a pretty high level and is foundational to the package itself, which includes Java, Scala, Python, and even R. And so what this allows us to do, and one other thing, it also exposes machine learning libraries exclusively in the package as well with this ML, Spark ML, and MLlib. And so what this really allows us to do is to have actually one platform to do both our engineering pipelining tasks as well as the model fitting, model prediction, data analytics tasks using all the same tools. It's nice in that it has a lot of kind of high-level built-in imperative and declarative abstractions. So analysts who prefer to write SQL can write SQL. You can do the things like the IBIS, Pandas type syntax as well, and everything will be able to execute on the cluster. It also has Spark ML, which provides some high-level models for doing machine learning that have been optimized for running on the cluster, which is important. So if you guys haven't seen Spark ML, this is basically what it looks like. This is using the Python interface. Again, there's Scala and Java interfaces as well. The nice thing is that for someone who's a Python user, a lot of the syntax actually should feel pretty familiar to you. There's concepts like these transforms. There's the concepts of the models. They all implement the same APIs. They have the pipeline API similar to Sklearn. And so you're actually working in Python, although you're operating on the cluster. And the Spark is handling, obviously, getting all the jars and all the necessary source code to all the nodes of the cluster. So that's pretty cool. And I think it's really interesting in that you can now fit models on all your data. You can predict on all your data. But again, this is very, very nice. But the problem is that you're still reliant on PySpark and what's available in PySpark. And there really is less capability and some subtle differences between that and what we use in the NumPy world, or Pandas world, or Sklearn world. It's a slightly different dialect, which can be a little bit frustrating because you are doing a little bit of context switching, but still it's not so bad running through switching from Java to Python, for example. But the big data extractions are very useful. You're working at you're able to do kind of functional programming on the big data using kind of things like map partitions, reduce by keys, group by keys, which are very powerful. And again, you're now bringing your code to the data, which just makes things much more scalable. So as we look through this, we said there's some really great things. Well, how do we actually combine kind of PySpark and the PyData platform? And there's kind of some nice things about PySpark is that you can actually write closures and anonymous functions. And so what we want to do is specifically try to build workloads that take advantage of using Spark and PySpark for all the high-level data manipulation, getting data in the right format, doing all the shuffling on disk, and then actually running our models through the PyData stack. And this works particularly well for us in that a lot of our models, fitting and predicting, are actually highly parallelizable in that we're normally only fitting and predicting on a subset of our data. So we can shuffle all the data around, get it on the right places, and run multiple instances of the same model on little subsets of the data. So this works pretty well. And we've built some tools, and we've open sourced some tools I'll talk about in a second, around helping us distribute Conda environments more effectively through Yarn and getting it on the cluster. So here is a very kind of simple example. So we're writing PySpark here, and what we have is we have a method predict, and what that method predict takes is an array, which is a features, and actually what would be a fitted sklearn model. And what this will do is we'll use this predict method, we'll query it with a pre-fitted model, we'll tell it the return type, and create a user-defined function in Spark. And what that allows us to do is then use the Spark data frames, the Spark abstractions that they built, and actually run our model using those abstractions, although it is an sklearn model implemented. So that's pretty powerful, right? Now we have all of PyData in a way that we can use within Spark, distributed on a cluster, and everything is written in Python. No translating between languages, no requiring intent rewrites, no sacrificing capabilities. We have kind of the best of both worlds in this example. So how do we do it? This is a kind of a basic diagram taken from the Spark documentation around how Spark works. But basically you have a driver program that kind of controls Spark context, you have the cluster manager, and you have your worker nodes where all the work happens. So the driver program is basically pushing out work to the workers, pushing out code, making sure the environments are ready, the cluster manager is making sure that resources are using correctly, and the Spark context is kind of managing across this work. So how do we actually do it? Well, basically we're using Yarn and Conda. We're packaging up our environments in basically the environment.yaml specification that Conda uses, and we distribute those through Yarn, and we have some custom code that basically will build those environments on the workers on demand. That is a pretty big change, because otherwise the alternative is you have DevOps, you have someone in your cluster team. I don't know. I don't know what they do. Maybe they're running around with a USB. We'll see. But they're actually responsible for having to put those environments on the cluster. This gives us the opportunity to define what are the environments that we care about. I'm doing some new geospatial work. Well, I can bring in a geospatial library to find my environment and actually get that out on our cluster to run our job against. That's pretty cool. And so we've kind of recently open sourced a project called Sklearn, and the project does a lot of different things, but it makes the interaction between Sklearn and Python a little bit easier because Spark is written in Scala. But it also handles this distribution of different Conda environments through Yarn. It's a relatively new project, I think just a few months old. We just open sourced it, so you can feel free to check it out or contribute. But it's really going to be, it's part of our data platform now, and we pulled this part out of the toolkit to basically give it back to the community. So lessons learned. Again, we kind of, right now, we get all the advantages of this using PySpark, and also now have access to the PyData task. With Sklearn, we now can actually distribute custom environments to the cluster through Yarn relatively easily. The one downside, though, is that it still does require kind of some low-level knowledge of how Spark works. So we're not completely free of just not having to think about Spark and big data. We're interacting with a lower-level API within Spark, typically resilient distributed data sets or RDDs when we're doing these types of modeling. But still, it's much easier than anything else that would be possible. Some final thoughts. I think one thing I didn't talk about today that I think is another use case which is pretty interesting, which is reporting, and how do you actually produce reports, which is another piece of our work. I think it's really exciting as you look around the community and attend these talks. There's a lot of interesting opportunities to change how we actually do reporting as well. And we're still trying to figure that out. But you look at the things that the Jupyter dashboard community is starting, went to that tutorial, look at the bokeh and what's available in those bokeh dashboards. Those are really cool. And I think it's also just extending how we can get the data and our code in the hands of our users with the smallest number of hurdles possible. And that's really exciting. So with that, I think I'm done with my 30 minutes and open up for questions.
Thank you, Josh. We have 10 minutes for questions. So there we go.
I was interested, you said it's bad to bring your data to the code. I didn't quite get what you meant by that. Can you explain that a little more?
Sure. So when we're talking about Hadoop world and what we do at MaxPoint is we have all our data on a distributed cluster in the data center spread across multiple machines. And this data literally is hundreds of terabytes. And so if you're running code that requires you to pull down 20 terabytes of data, that takes a lot of time. The flip side is you take your source code, which is 10 or tens or 20s, hundreds of kilobytes, and taking that to the data. That's much more efficient. Not to mention all the shuffling and those type of things of reading from different machines. It's just much easier, much more efficient to bring the small data, which is the code, to the big data, which is living on your cluster, than vice versa. That's what I meant.
I understand there's a big performance hit when you send Python out to the cluster because it's got to spin up Python workers, it's got to serialize, deserialize all the data back and forth to those worker threads. So I've been trying to avoid that. Can you speak to that a little bit?
I think you're exactly right. I mean, all the remote procedure call, this translation and things that I was talking about when we were doing the interactive workloads that we're doing through Thrift, that still is happening in the PySpark world. Spark is natively on the JVM, and it's handling this kind of through some pickling magic, getting your code everywhere, and you're paying a penalty for doing it. And I mean, the question really is, and maybe it's always for kind of optimization, is what do you want to optimize? Are you optimizing developer time or computer time? And I think what this allows you to do, though, still, is make that a conscious decision and decide when you want to move from caring about your developer time to caring about your computer time. The nice thing about the PySpark Spark ecosystem is that Scala is actually relatively close to the PySpark syntax. And so migrating things from PySpark exclusively to Scala Spark isn't a huge lift. Obviously, it requires people to learn new things, which I may be implied. But transition your PySpark jobs to Scala Spark isn't as awful. I mean, devs would probably say this rewrite is still the worst, but not the worst I've ever seen. You can't really. It's harder to solve that with combining Spark and the PyData stack, though, when you move to Scala.
Follow-up question.
Sure.
So I found that the sklearn library is far superior to the Spark machine learning. Is that one of the primary drivers of this effort, the Spylon thing?
It's a key piece. I mean, it's hard to write big data machine learning algorithms that kind of can parallelize across machines. And so I think sklearn can move a lot faster, frankly, and it's been around more. So it is a big piece. I mean, it also is enabled by the fact that we do have these kind of parallelizable workloads that actually don't require us to read all our data in simultaneously in fit models. But yeah, we want to be able to use sklearn because it has a lot more capabilities than just Spark ML out the box.
A quick question. I work in a Microsoft .NET shop. How much of this is portable over to a Microsoft ecosystem?
I think, well, especially the interactive workloads, I can say for sure is. I mean, well, I shouldn't say for sure. I'm pretty sure that the thrift bindings support things like C#. And so that part would work basically the same. I don't know if anyone has any kind of large scale Microsoft Spark implementation, so that's a little bit outside of what I understand. But I think from the interactive workloads, the model still upholds.
I can.
Yes.
What is Python?
That's a good question.
On the spot from the youngest member of the conference.
Yeah. So Python is this magical thing that allows you to be able to do so much more than you ever really realized was possible just by typing on your computer.
Wow. Yeah, nailed it.
I don't really understand all that much about how thrift works, but can you give me some idea of like what kind of throughput can you use thrift for? Is like this high volume, and does it have any kind of fault tolerance or handling?
Yeah, I mean, it's definitely not a high throughput type interface there. You are kind of buffering and working these different protocols and how you transfer it, but it's definitely not really designed for high throughput workloads. I don't really think there's any fault tolerance, those type of things as well. Yeah, it's mostly for smaller data for our works. Yeah.
I guess this is more of a suggestion / plug for something.
Sure.
But if you're using Thrift, I saw that you guys were using the official Apache Thrift implementation. There's a library called ThriftPy that is a pure Python Thrift implementation. And it's actually much, much easier to use from Python. And you can actually import your Thrift files. Like, so that spec you have, you can do like import whatever .thrift, and it will make a magic Python module for you on the fly.
Well, that's cool.
So I would recommend that.
That's cool.
Any downsides to that?
It's very slightly slower than the Apache implementation, but it uses Python, so it's like, very, very slightly.
It's cool. I'll check it out.
Yeah, with regards to I guess you called it the microanalytics services, I was curious about the debug experience. Like if there's bugs, it seems like you'd need a combination of skills on both the engineering and the data science side. And so could you comment a little bit about that experience?
Yeah, you're right. And I guess I probably glossed over it a little bit in that, you still have to do some of the non-functional requirements in your Python code in these microservices. Logging, for example, handling kind of error messages and passing them back through. So you do still have to think a little bit about some of those things, and it does require a mix of skill sets when someone's interacting with your service and something goes wrong. And I think it's worth it, but it's not a perfect solution in that regard. Yeah.
Is there robust error handling in the thrift layer itself and good error codes to look at?
You actually have to build your own exceptions. There's an exceptions, constructor in Thrift, but you're basically constructing your own exceptions here. They have some base ones like transport exceptions, those type of things. But any custom application code that you want to be able to handle error handling on, you're building your own custom exceptions. Yeah.
All right. And with that, let's thank Josh.